So I wanted to take a few moments to do a couple examples from the applications of logarithms and exponents chapter. You will be given these three formulas. Compound interest, here's your formula. You will not be given what each letter specifically stands for. You will have to know that. You will just be given a sheet that looks exactly like this. So you'll be given compound interest, compounded continuous, and carbon-14 dating, and then you'll be given the constant K down here. So you'll need to know what each letter represents, but you do not need to sit down and memorize these three formulas. So here's our first example. This is not one that's out of your homework set or in the notes. I wanted to give you an additional example, so that's why it's just example 1 and not assigned to a specific number. But if a fossil contains 1/5 or 20% of the carbon-14 contained in a contemporary living sample, estimate the age to the nearest 1,000 years. So you'll see in your textbook it will say 2 significant digits. Estimate the age of the fossil. So how old is it? So you will be given the formula. You'll see it right here on your screen, and you will be given the K. I recommend you just go ahead and use the decimal version instead of the natural log of 2 over that whole thing. Just use this decimal. You will be given the decimal if for some reason you forget it and you are using this in the outside world. Just type it into your calculator. It will give you off this decimal anyway. So I'm going to go ahead and plug everything in. That 1/5 or 20% that you see in the first sentence, this thing tells me that A of t equals 0.2, so I have to change 20% into a decimal, 0.2 of A0. Remember, A0 or A0 means the starting amount of carbon-14 in this case. So I'm going to take this and replace A of t with 0.2 A0. So I'm going to replace that and then finish out the other half of my equation. Also, I know K, it's going to be anytime you see carbon-14, this K is going to be the same. So where you have a K right there, I can replace it with this decimal. And then my T. So there is your now equation. Once I've plugged in the 20% or 1/5 and then also the K. So now I'm going to go through and divide out the A sub zeros because there's one on each side. Those will actually cancel, leaving me with 0.20 on the left and then E and that crazy decimal. Now remember, I'm working on solving for T. So I need to get t out of the exponent. And if you remember, we had a property that said that that e and natural log undid each other. So if I go through and natural log both sides, I'm going to actually be able to cancel out the e, and it will bring everything else down for me. So I've natural logged both sides. Now, because I natural logged, the natural log and E are going to cancel out. So I'm left with natural log of 0.20 on the left. That's just some number. And then this on the right. Now I have some number times t. Well, to get rid of something times t, I'm going to divide both sides by it. And then those will cancel out on the left, which I will type that thing into my calculator and get 13,235.509. Now, that's what my calculator said, but if you remember way back in the directions, it said to give me 2 significant digits or round to the nearest thousandths. So actually all I need are these first two, that's the thousandths. So my final answer is going to be 13,000 years. And the reason we round to only to two significant digits is because this is a big estimation, and so scientists just then round all the way down to the nearest thousandths, or if the next digit is 5 or higher, round all the way up to the next one. So that's why we have kind of some loose answers there. So here's our second example. It's number 22 out of your textbook. It's also in your notes. The problem says the concentration of some bacteria B in millions per milliliter after X hours is given by this equation. B of X equals 1.33 E and then raised to the 0.15 X. So there's your equation. It'll always be given with bacteria. This is an example of exponential growth versus the last one where carbon-14 decays over time. Bacteria duplicate over time exponentially. So this one will be your exponential growth example. The first part says, well, how many bacteria will you have after 2.5 hours? As soon as I see something about hours, that tells me immediately that I'm plugging into X, because if you see up above and in the directions, it said that X is the number of hours. So I'm going to fill into my equation, and instead of writing X, I'm going to write 2.5. Don't need the units. Now this thing, you just plug that right-hand side into your calculator. Once I plugged it in, I got 1.935, and so you can round that to 2 decimal places. And remember, that's the number of bacteria, so it's 1.94 million per milliliter of solution. That's just how they measure bacteria. So the second part, B, says, well, how many bacteria will I have after 8 hours? So it's going to fall exactly the same. So you're going to plug it into your calculator. Make sure if you're using especially the TI-83 or the older TI-84, when you plug this thing in, you have to put one big set of parentheses around the entire exponent. So you would type it in like that into your calculator. Just if you don't, it's going to do crazy things. So make sure you put both of those numbers in one big parenthesis. So once I typed it in, I got 4.42, and again, that's the number of bacteria, so it's million per milliliter of concentration. So that's how many bacteria are in that little area. All right, so here's the last part of this. Part C says, after how many hours will there be 31 million bacteria per milliliter? So now the question is changing. A and B were asking me how many bacteria would I have. So I was looking for the N, the B of X, how many bacteria. Now notice this one is saying how many hours. So I'm actually going to be solving for X this time around. 31 million bacteria. That's going to go into my B of X. Because that's a number of bacteria, that's going to get filled in for B of X. So the question's changing. I'm now solving for X instead of for just typing it into my calculator. So I've filled in my B of X. So I have 31 equals that whole thing. Now before I natural log both sides, because I see an E, I need to get something out of the exponent of E, and that we've saw in the past few examples. I'm going to natural log. I want to get rid of that 1.33 first. So I'm going to actually divide both sides by that, and then I'll have E by itself, and then I can undo it. So I typed that left thing into my calculator, and I got 23.30827. I just wrote down a whole bunch of decimals to prevent some rounding error. Now that I have E by itself on the right, now I can go through and natural log both sides. Natural log and E, that property says they cancel each other out. So on the left, I have this big long number, which is just some number, and then the E canceled, 0.15x, going to divide by 0.15, divide by 0.15. I'm going to type that whole thing into the calculator, and then that will be what x equals. So I typed it in and got 20.992055. Your answer may be a little bit different if you use that exact answer over here on the screen, whereas when I typed it into my calculator, I did ln of second, the answer button, so it may look a little bit different, but we're going to round off to the nearest whole number just because, again, it's an estimation, so the final answer is going to be 21 hours until there's 31 bacteria. So that will be my final answer. It will be very clear on the test. When do I want you to round to 2 decimal places versus when do I want you to round to whole numbers? So just make sure you read the directions. It should be very clear. And as always, if you have questions on how to round, just ask me.